Hello, this is a module from the University of Washington. My name is Kyle Wistron, and I'm here with the instructor of this course, Info 445, Advanced Database Design, Greg Hay. He came up with this course, and I'm his TA for this quarter, and I'll be leading you through indexing. So we're going to start with the question, what is an index? If we have a large collection of information, this happens to be actually a book that someone printed of every Wikipedia article that's ever been written. So if we have this giant book of information and it's not in any particular order, it would be impossible to find any given piece of information without looking through the entire collection page by page in order. So what does this look like on a database? Well, if we are asking the question, what is David Smith's email? Essentially we have to go through every single record in the table and say, okay, is this David Smith? No. We have to go to the next one. Is this David Smith? No. Is this David Smith? No. Is this David Smith? No. Is this David Smith? It happens to be yes. And so then we can find the value that is under the attribute of his email.
Now, what happens if there's 10 million rows in that exact table that you were scanning and you find David Smith at row 7? Do we stop or do we keep going?
The unfortunate part of an index scan is if it's not guaranteed to be unique, we'll continue to scan through the table just in case there's another occurrence of a record with David Smith in it. So in that case, yes, every single time we look up something like first name and last name, we're going to go through the entire table to see, because we're asking for every single record. Now we can try to combat this by using the keyword top one, but if we omit that, it'll scan the entire table every single time. And so of course this pattern is just an example, and the actual execution plan is determined by the query optimizer, and that's going to depend on your database configuration and the particular way your query is called, but in a lot of cases this is what happens. So what is an index? We're back to this question. So to combat this in print, in books, or in newspapers, journals, things like this, we use indexes that contain references to pieces of information in alphabetical order, so that way it's easy to find, and for every value we have pointers to where we can find the piece of information in the book itself. So if we're looking up Theodore Adorno, we know that we're going to go to page 53 because we have the value that we're looking up there and a pointer to where we can find more information. So when we talk about databases and indexes, we have two types of indexes. They're known as clustered indexes and non-clustered indexes. The book that we're using calls them primary and secondary indexes, but in industry we use the words clustered and non-clustered, as we'll talk about in a second. For clustered indexes, each table in the database only has one of these clustered indexes, because it determines how the data will be physically stored or clustered inside the computer, usually on a hard disk. In SQL Server, if you assign a column as a primary key, the clustered index for that table is going to be on that primary key automatically. And in our book metaphor, this is like organizing every chapter in the book in some specific order, whether that be chronologically or in the case of something like a journal, we'll do it alphabetically by article title or something like that. Depends, depending on what what the publication is, and you get the idea. With this in mind, it's important that your primary key value be narrow, and this means that we want to make it as small as we can. We want to make sure it takes up the least amount of space on disk while maintaining uniqueness. This is to optimize the amount of space it takes on disk and in memory, because the smaller the footprint of the value, the more values we can fit into our limited memory space, and that maximizes the number of values that we can access in an immediate basis. So
now this is a composite primary key.
Yeah. So this so a perfectly relational method of forming a primary key would be to create a composite key like this. And this is, in this example, it's a user's first name and a last name. However, because this key is likely to be comprised of two varchars, It's going to take a lot of disk space for the key itself, and therefore the index is going to take up a lot of space too. So a better way to do this would be to use ints for surrogate primary keys, and this is kind of considered the de facto standard, I think, because it's much better to use a single int as a surrogate key because it does take up significantly less space, and it gives us the benefits of sequential and non-changing attributes that we'll talk about in a second. So another aspect that is important to think about when identifying a primary key is to use a clustered index to ensure the values are sequential, or excuse me, it's important to use a sequential key as a clustered index. So since the clustered index controls, if you think about it, where the data is physically stored on a disk, to give us the highest write speed possible, we want to make sure that each write we make is as physically close to the last one as possible. So this is important primarily on hard disk drives where we're actually having to move a spindle across a platter to where we want to write. If we write sequentially, we don't have to move that spindle across the disk to a new record. There's just a finite amount of movement that we have to make with that spindle, if at all, to write the new record. So on those hard disks, it takes time to physically move that spindle, and if we can minimize that as much as possible, we can really speed up our write times. So, however, the sequential primary keys on an index also give us the benefit of not having to reorder the data once the data comes in, which also saves processing time. And the easiest way to accomplish this is to use, as your surrogate primary key, an integer, like we talked about, that is set to auto increment. And we do that on SQL Server with the identity property, so that automatically increments an ID value for you every time you insert a new record. So you don't even have to think about it. It's taking care of things for you in the background. So the final thing that's important to think about when defining a primary key that we're going to index on is to make sure it's a value that's not going to ever change, because if we have to go back and change a primary key value, since the index controls where on disk that data lives, that means that we'd have to go back and resort all the data again, which means potentially moving a lot of records, and that in turn means a lot of processing time. So this is also easily solved by using an ID integer as a surrogate primary key, because it has no relation to the data itself, and there would be no reason to update just an integer anyway. So the de facto standard, it turns out, is to use an integer for your primary key with the identity function in SQL Server, and that ensures that your ID value for your index will be narrow, sequential, and never changing. And remember, if you define that ID as a primary key in your table, it's automatically going to create a clustered index for you. So you really don't have to think about it. You're going to get that benefit automatically. So we talked about clustered indexes, or primary indexes. What's next? We have non-clustered indexes, or as the book likes to refer to them as secondary indexes. So non-clustered indexes are different from clustered indexes primarily because they're completely separate. It's a separate structure from the data, meaning they don't actually control the way that the data is stored, but rather it provides information about how to find a given piece of data. So in this way, we're following our book metaphor. If we're following it, the non-clustered indexes are really what we think of when we think of an index in a book. So it's that part in the back of the book that gives you a reference to where to find more information. While clustered indexes happen more or less automatically, non-clustered indexes are something that has to be explicitly addressed when building a database. They're comprised of a single attribute or a set of attributes that are ordered, so we can find them easily, and then they point us to where we can find more information on the records containing a match for those attributes. So usually we query on names and foreign keys the most in our tables, so these are usually good candidates for a non-clustered index whenever we're filtering on a query, and we'll go over that near the end of the lecture, give you an example of that. We use non-clustered indexes primarily on tables where we have these specific queries that we use repeatedly, and that helps us to optimize the way we find a single record if we're trying to do that a large number of times in a given minute or day, as it would be. Because we don't want to have to scan the table to look for any single record based on a name or whatever, we want to be able to sort of take a look in the index first to see if it can tell us where to look first, and that will give us a significant shortcut to finding the data. So this isn't necessarily helpful for queries where we will return a large number of records, because in these cases the query optimizer will usually choose just to do a scan instead. Greg, do you want to?
Yeah, so non-clustered is intended for finding filters, columns that are filtered in the where clause. We're not often looking for, it's going to be a last name. We're going to be filtering on a last name. We're not always looking for perhaps the primary key, because we don't think in terms of primary keys. We think in terms of names. We think in terms of dates, object. Dorm equals McCarty or McMahon. So if it only returns, let's say 50%, if we have a 100,000 rows and the filter is evenly split between McMahon and McCarty, that would not be a very wise column to index on, because it's not highly selective. Highly selective is when we get down to around 5% of the rows returned. So if it's 100,000, an index should filter out, or our query should filter out 95% of the rows. So we're only dealing with a small amount.
Mm-hmm. Yeah. So So that's important to remember. And in the query, when we examine the query plan, it'll tell us about how much we stand to save the impact of an index if it detects that there's a missing index. And I'll show you that again near the end when we do our preview. But I'll also note that you can put several non-clustered indexes on a single table. And this is to optimize it if we plan to do more than one query that will be run several times very often. So Greg gave an example, but I'll give another example. You might have one query that gets users by their full name, like in our email example. To best, if we want to prevent full scans of that table, we'll want to create a non-clustered index for full name. But what if we want to make a login store procedure that just is provided an email address, and we have to look up a user's name from an email address? Well, in order to prevent a full scan for the email address, we'd have to create another non-clustered index. So we can create non-clustered indexes on both attributes separately. The caveat to this, though, is that every time you insert or update data in a record, the database management system will have to update that index accordingly, and that means that it might have to shift things around. And although it is much faster than if we were editing keys of a clustered index, since for non-clustered, we're not moving the actual data, this reorganization of the non-clustered index can take some time, especially if there are many of them. And so this is why OLAP systems make good use of non-clustered indices. Since the data isn't changing, we can throw as many indexes in there as we want, because they greatly decrease the read speeds, and we don't have to worry about needing to reorganize them because of new data. With OLTP, on the other hand, this is it's a genuine concern, and if we pile on too many non-clustered indexes, it can greatly increase write times, and it can, in some cases, the query optimizer may just ignore them together. So it's just something to be mindful of, and only put indexes on attributes that you're gonna use often. So that's the difference between two types of indexes, but question is, how are they stored? How are they stored in the DBMS? How are they stored on disk? Well, we can talk a little bit about that, and we'll do a little caveat here. This is more of a logical explanation of it, but for the most part, this is how indexes work. So For both clustered and non-clustered indexes, they're stored as a balanced tree. If you've taken an algorithms class, data structures algorithms class, you'll know that this just means that the number of records on either side of any given node will be the same, given there's an even number of records. So this is the idea that it builds out instead of down. Um, the tree is only comprised of 3 layers. The bottommost layer is the leaf node. It's comprised of the leaf nodes, and we'll talk about that. Since the clustered indexes control where the records are stored on the disk, the leaves of a clustered index are the physical database pages, or logical, they're the actual database pages on which the actual data is stored. So when we look at the leaves of a clustered index, we're actually looking at the pages in the DBMS that the data is stored on. So each page is logically contiguous, meaning that each page continues the previous page. And ideally, these are physically contiguous on disk too. This doesn't always happen, but ideally, they're physically contiguous. And since each page can only hold a certain amount of data, as soon as one page fills up, the writing begins on another page, given your key is sequential. And the range of ID keys which are stored on each page and a reference to the page is stored one level up in the tree in a layer of what we call branch nodes. So we go from leaves, now we're going up to the branch nodes, which is a little bit, if leaves are the fine data, we're going up to the branches, which are slightly more coarse. So each branch can have references to several pages, but for each page, the branch knows the range of the ID keys stored within them. So a request for any given ID can be routed directly to the correct page without having to look at any other pages. So if we are given a key passed in the branch node, it'll tell us which page that key fits into, because it knows the range of the keys for each page.
Now, I'll just add to that real quick. You explain it from the bottom up. Typically, the way that an index is traversed is top down. So we're given a root node. We will traverse down. First, we'll scan perhaps at the root level, find the appropriate range of values. Let's say our value is 604. We're going to scan past the first node, enter at the second node, because the value we want, 604, is between 501 and 1,000. Then we traverse downward. 604 happens to be in the first branch node that we encounter, which is going to be between 501 and 750. We then scan the leaf node until we reach 604. That may seem like a lot of work, but it is actually significantly better in overall performance than if we had to scan the index in its entirety.
Yeah. So the final layer, like Greg said, the final layer above the branch node is the root node. This is the entry point of the clustered index where the total range of ID keys for each branch and a reference to each branch is stored. So this is the clustering key, the physical address where we start searching for a clustered index. In this way, a request for a specific ID key can be routed to the correct branch from the root, which in turn can be routed to the correct page that contains the record with the given ID key. This is what we call an index seek, and it's much faster than a scan because it drastically cuts down on the number of pages we have to read before getting to the data that we're looking for. So, for example, if we're looking for a record with the ID key of 752, with a scan we would have to read through each individual record in every page before arriving to the one that we're searching for. But with an index seek, utilizing a clustered index, we start at the root, which directs us to the branch that contains the pointers for the pages with ID keys 501 through 1000. And then the branch points us to the specific page that contains the ID keys 751 through 1000. And then we have to read at most only 250 records in this case. That's the amount of records are in the page before we get to the data that we're looking for. So it's important to note that there will always only be one root node, so we always only have one entry point, but a single root can reference many branches, and that in turn can reference many pages each. So at some point, for very large databases, this can lead to fairly good granularity, when searching for a specific record. And we will only need, we'll pretty much only ever need one layer of branches, unless our ID key becomes so big, we have so many records that we have more than 2.37 billion, which is the limit of the int data type. And at that point, we'll just need to develop a new layer to avoid those overflows. So that's an overview of clustered indexes. Let's take a look at non-clustered indexes now. So the structure of non-clustered indexes are almost exactly the same as clustered indexes, except for in the leaves, where clustered indexes store the actual data for the record. Non-clustered leaves only store machine addresses of the leaf node where that data occurs in for the clustered index. So this gets a little bit complicated, and it's a little bit ambiguous, even to professionals, from what I've understood. But the important thing to note is that in the non-clustered index, it's very similar to the structure. We start at the root, which has coarse groupings of whatever key that you created an index on. So in this case, if we were looking for David Smith, we know that David occurs between A and JO, so we can get a pointer to that branch, and we know that it occurs between BEN and JO, and so that leads us to this leaf, and that it'll give us a page which will have a machine address that we can look up, and that'll bring us to the clustered index. But in this case, we can see that essentially it'll bring us to the data that we want. It'll have the effect of sorting this data in alphabetical order, essentially. This is not what happens physically, but logically this is what happens. So I'll go over how we put it together here. So this is an example. Again, if we're looking for David Smith's email address, well, where do we start? So we always start, if we're given one, we start at the non-clustered index. So we start here. We know that David Smith's name starts at D, and we know that that's between A and JO. So that gives us a reference to this branch down here. And because we know that D is between BEN and JO, we know that we're going to go to this page down here, and that's going to give us a reference to the address where the clustered index root, it's called the clustering key, where that is. And so we can take that. In this case, we're just gonna use as an example. This isn't how it actually works, but this is an example. We're going to take the ID value that it's given here, and we're just going to run that through this. This is our clustered index now. We're given the ID 501, so we know that 501 does in fact fall between 501 and 1000. Point us to this branch. We know that it falls between 501 and 750, and that's how we get to the actual data page where David Smith's information is stored. And that's how we get his email address or their email address, and this is what we call an index seek. So this is, as you can imagine, it's a little bit faster, quite a bit, well, not a little bit faster, for depending on the size of your data. Once we get to bigger sets of data, it can mean great savings in time, as well. I'll show you an example of that a little bit later. But this is an index seek as opposed to an index scan. It's a lot faster. It's great. It's what allows us to find data very fast and reduce wait times. So next we'll go over an example query. So this is an example without an index. If we're asking the database, we have a table full of customer information called TBL customer, and we want to find the information where the first name and the last name equal these specific values, or any value in this case. It doesn't matter what the value is, it'll still be generally the same, because we'll have to do an index scan, as you can see here, through the entire database, or through the entire table rather, and we don't have a top one keyword on here, so in this case it will search through the entire table to see if we can find any more records, even if we've already found one. So it's going to literally most of the time it's going to literally look through every single row, every single record, and once we find it, great, but we got to find if there are any more, so it's going to keep going. If we add, or let's take a look here. I took a screenshot. This is an execution plan that we can get from SQL Server, and it's telling us that exactly that. So it's telling us that it performed an index scan, and that the estimated CPU cost of this operation was just about 1/10 of a second, so greater than 1/10 of a second. And if we look at the estimated operator cost, which is a couple lines above, 1.4. So that's just remember that number. The next slide is with an index. If we add an index, we can do the same exact query, but in this case, if we look at the execution plan, it's doing an index seek and a key lookup. So an index seek on our non-clustered index and a key lookup on the clustered index. We got a key from the non-clustered index from the leaf node, and we put that into our clustered index. We can see that the initial index seek took, what is that, 0.0001 seconds, 15 seconds, so round that to 0.0002 seconds. And then our key lookup was 0.00, about the same, 0.0002 seconds. So add those both together, you get 0.0004 seconds, which is significantly faster than 0.1 second in this case. So even though it's separated it into two different operations, it's significantly much faster thanks to those indexes. And if we look at the operator cost, it's combined, it's 0.006, which is a whole lot less than 1.4. So and this is just to show that we can really reduce CPU cost, I/O cost, operator cost, things like this with indexes. Do you have anything to add, Greg?
Well, yeah, just that as we increase the number of rows, we will see more significant benefit, not just in actual time, but in percent of improvement. And it's not linear. It is exponential or
Logarithmic.
Logarithmic. It is. There's just a basic cost in assembling or traversing through the indices to find the data or getting the pattern set up, and then after that we can rip through it very quickly and see incredible differences, 1,000-fold increase in performance.
Yeah, so now let's, the important thing in creating a database and optimizing it is how do we identify where to put these indexes on. So as we talked about, clustered indexes are more or less automatic on the primary key, and that's great if we use an integer. But in this case, the question is how do we identify where to put non-clustered indexes? So in this case, this is the same example on our customer. Well, this is a little bit different example actually. We're still in the customer table. We're looking up on first name, last name, date of birth, and email. So this is an example query execution plan. As you can see, it's doing an index seek, or excuse me, an index scan, which, as we discussed, is certainly a very slow way to do this. But we did do top one, so it's not searching through the rest of the database once it's found a value. But still, it has to search every single record until it finds the given value, and that can be a lot of times the slowest part of a query. The great news is that if SQL Server, if the query optimizer notices this, it'll tell you verbosely that it's missing an index, and you stand to gain 99% improvement if we add an index here. So in this case, it even tells us exactly what we need to do to create an index. In this case, because we are using the where clause to filter on first name, last name, date of birth, and email, it stands to reason that it would be pretty beneficial to add a non-clustered index on these values. And this is exactly what it's suggesting we do, is create a non-clustered index on first name, last name, date of birth, email. And so the code is there at the bottom. It's literally create non-clustered index name on table, and then the columns, the attributes you want to index on.
Now you're having more than one index, more than one column in this index. So that is often not obvious that we can have multiple columns in a single index.
Yeah. So you could have the option of only indexing on first name, but that would, the only instance where that would add a lot of benefit is if we just had a where clause with first names. If we were just filtering on first names, and it might help other queries too. But if we know that our query, if we're in this case, in the case of this database, in this example that I'll show you in a second, we never search just on first name alone. There's no reason to. In our business case, there's no reason to search on first name alone. We always search on first name, last name, date of birth, email. So it adds a lot of value for reads. So this is why we do it. Let's go to a demo here. How does that sound? So I have here on my virtual machine a database that we just created. It's example. It's an online store where we have customers, we've got products, we've got carts for users to store their products in that they want to buy. Once they order those items, we can keep track of them in order, and line item, payment, username. Those are other tables that we have, but we won't be interacting with those today. If we run a query, we have a synthetic wrapper here for adding to cart. So basically what this is going to do is we're putting 1,000, we're asking it to do 1,000 transactions for us in this case. So let's go ahead and get that started. What this is going to do is it's going to get a random customer and a random product, and it's going to put that into our normal store procedure that we would normally use to check out a user. So this is just a way to stress test our database here and see how long it takes. And this helps us do optimization and things like that. So in this case, it's going to do that 1,000 times. So it's going to look up 1,000 random users, 1,000 random products, and put that into the user's cart. Okay, so there we go. It just came back. Let's see how long that took. It took 35 seconds. Okay, that's not too bad. I thought it would take 45 seconds, but we're having a good day here. So 45 seconds. That's not bad for 10,000 records. That's not bad at all. If I were to argue. Let's take a look at the query plan or the execution plan. So let's just set that to 1 so we don't get a whole bunch of it'll help us make the execution plan more easily understandable. So the large portion of this store procedure is just getting the row count for the customer table, which that's just for our synthetic store procedure for testing, and that wouldn't happen in production. But our second most strenuous activity we're doing right here, as you can see, 48% of the time it's taking is just in getting the customer ID. So if we look here, it's doing an index scan, so that makes sense. That makes sense as to why it's taking a long time. The scan itself is taking 91% of this 48% of the entire query. So this is 91% of this part of the query, and then this part of the query is 48% of the entire execution plan. So we can see that, yeah, that's taking a long time. If we look at how much the estimated CPU cost is 0.1 seconds. We can optimize that, I think. And same thing with the product. It's only 3% of the query, but it's still saying that we stand to gain we have 96% improvement on this, and that's obvious because we have an index scan here that's taking 92% of that query. So we can. I am willing to argue that we can bring this down quite a bit here to uh, less than 10 seconds, I'd say, for 10,000 rows, if not faster. So thankfully, like I said, this is cueing us in here that we're missing an index, like we saw in the slides, that the impact we stand to gain is 96% and 99% respectively for these two queries. So that's a lot of gain for us. We should be looking at that and saying, wow, we have a lot to gain to create these indexes. And it literally tells us what to do. It's very very verbose in this case, but if there's ever any doubt as to what your indexes should be comprised of, it tells you right here. And in this case, like I said, in our slides, we're always searching by first name, last name, date of birth, and email. So that's no surprise that it's asking us to do an index on those. And for our product, we search on product name and release date. Those two attributes together create uniqueness for us, other than the primary key. But so that's what it's telling us to index on there. And it just so happens that I agree with them. So we'll go ahead and create a non-clustered index. I have the code right here. This is the same code that we saw in the slides. Create non-clustered index on the table customer on first name, last name, date of birth, email. And this doesn't take any time at all. We'll just create it. We have about, I think 100,000. I can't remember. It was at the beginning here, but quite a few customers and quite a few products. We're creating a non-clustered index on product name and release date. We'll execute that. No time at all. Now if we come back down here to that same exact store procedure, synthetic wrapper, we're going to do 10,000 rows again. So 10,000 rows. This is the exact same query that took, what did it take? 35 seconds last time. We're going to run this now. We're going to see how fast it's going to take. So I'll do a countdown here. This is going to be exciting. Here we go. 3, 2, 1, go. And we go boom. And we go boom. And we go boom. Here we go. 4, 5, 6, any second now. There we go. What is that? 7 seconds. We went down from 35 seconds to 7 seconds on that query. So
try it again. See if it should be in memory now. And if you run it again, it might go faster than 7 seconds a second time.
6. It'll get faster once you know this. It just so happens that we have. Let's see how many customers we have in this table. So is that 100,000? Yeah, that's about 100,000. So it's there's a lot of customers that it's got to go through. But so next I'm going to actually pause the video here because I'm going to set this to 100,000, and I'm going to actually recreate this database so there's no indexes on it at all, and there's not going to be anything in memory. And then I'm going to run this 100,000 times. I'm going to do 100,000 inserts, and we'll see how long that takes, and then we'll do an index on it, and then I'll see how long it takes after we add the index for the same amount of rows. So I'll see you in a second. Okay, we're back here, and it took, let's see, we did 100,000 rows in this synthetic store procedure, and it took, let's see, 6 minutes and 19 seconds. So that's just about pretty much linear, I think. If we multiplied the number of rows by 10, and it was 35 seconds to begin with, so that should be about 6 minutes. So yeah, it's pretty linear. Now we're going to do the same thing as we did last time. We're going to add these two indexes on customer and product. We don't have to look at the execution plan this time because it's going to be the same as it was last time. We just changed the amount of rows that we inserted. So now this is the same amount that we just inserted, but this time we have indexes. So we're hoping this will go a lot faster. I'll wager under 20 seconds, but I wouldn't be surprised if it happened under 15 seconds. So let's see what it is. Can we get a countdown?
Drum roll.
3, 2, 1, here we go. Okay. Every second here is hair raising. We're at 7 seconds, 8 seconds, 10 seconds, 12 seconds.
Watch it take 3 minutes.
Well, that should be pretty fast. Let's see. How much was it? Last time was it like 7 seconds, I think, when we did it with 10,000 rows?
Yep.
Let's see here.
Now, it is a virtual machine. It is relatively underpowered. It's a lawnmower trying to run a highly performant software. And now we're going to get up to about a minute. This is going to not be as dramatic. We might be able to make it better. We might find a better index here in just a second. We might go last name. Boom. So 1:03. That's not as logarithmic as I was hoping, but as we can see, it is still 1/6 the expense, 1/6 the cost of. Without an index, it took 6 minutes and 19 seconds. With an index, less than almost exactly 1/6, right?
Yeah.
Which is better.
Yeah, I don't think that's anything to shake a stick at, certainly. But you know, you can there's an art to futzing with indexes, and if you can find an index strategy that works for you, you can make it really go fast. And there's other things. It depends on your database configuration and how things are set up, but generally, you can make strides just with indexes on speed. So, if you wanted to do another quick example here, you can probably cut out watching if you're getting a little tired here. But let's do another one. In this case, we have checkout. So this is going to take items from the cart and turn them into orders for a user. So we're going to do 1,000 of these. So since we have 100,000 items in the cart, there should be plenty to check out. We're only doing 10,000 here, so we should be able to run this query 10 times, ideally. So this is, again, we have an index on customer and product, but we don't have an index on cart and payment. We don't have an index on payment either, which is required for checkout. So this should take, I tested it a little bit earlier, it should take about 1:45, 2 minutes. Let's see, we're at about 45 seconds here. So this is doing just about the same thing as the add to cart is. It's going to take a random user, and it's going to, or I can't remember if it takes a random cart or a random user, one of the two, but it's going to check out a single user, put all of the items in the cart. It's going to look at the current cart for a random user, and it's going to iterate through their cart and put them into an order. It's going to find the payment method for that customer, and it's going to associate that with the order. It's going to calculate a total price, and then it's going to put an end date on the cart, so that's an update. So all that together, there's a lot going on in this query, and that's why this is by far the most expensive query that we have in this database. This is actually the database that I developed over the summer for the certification class that I took, and we got this really roaring by the end of it. We're getting up about 2 minutes. If I am lucky, we should be getting around to the end. But again, we are on a quote lawnmower, and we're waiting for it to wake up a little bit. It's in the afternoon here, so getting a little sleepy. I'll go ahead and pause the video, and I'll come back when it's done for you. Okay, we're back, and it looks like this query took about 13 minutes 45 seconds. So That's quite a bit longer than I thought it would be. So that probably indicates that there is, in fact, something going on in the server that's beyond my control. I was thinking about it. I believe last time I logged in, it looked like it was wanting to do some updates. So perhaps it chose 6:30 in the afternoon to do some updates. But you know, let's see if we can cut that down. I've identified some indexes here that I think might help. We already have the indexes on customer and product, so let's just add the rest of them here. Create those real fast, and that's good. So we'll do the same amount, 10,000 rows. Let's see if it goes any faster. Let's see. Originally, when I tested these, like I said, it took about 6 seconds with all the indexes. It was very fast. Oh, look at that. Wow. That was 10 seconds. Wow. That was what I was looking for. We went from, oh, wow. I don't even remember how many seconds that was, how many minutes it was. It was more than 10 minutes, down to 10 seconds. So, yeah, that's just showing you right there how we can take a query that is very slow, very intensive on reads, and make it real fast just by adding in some non-clustered indexes. So I hope you enjoyed that. If you have any questions, feel free to ping me or get in contact with me. You can find my information on Canvas. Or, yeah, I'll see you in class next week. Hang in there. Hope you enjoyed it. Bye-bye.